Okay, and our second speaker is Manus Visser, who's going to talk about partition function for a volume of space.
All right, thank you very much for inviting me. So I will talk about work that's based, work in collaboration with Ted Jacobson, and I think it ties nicely with the presentation by Laurent, because I will also talk about finite regions and their associated gravitational entropy, but I will actually derive it using different methods, namely using the gravitational path integral. So the motivation comes really from the Bekenstein-Hawking entropy, which I think gives us a key insight into quantum gravity from low energies. So the Bekenstein-Hawking entropy is proportional to the area of the boundary, and it is indeed a quantum gravitational effect because both h bar and g appear in the formula. Now, it was originally, of course, discovered for black holes and later for cosmological horizons, but it is actually a very universal formula because it also applies to acceleration horizons, and arguably, as Laurent also mentioned, it applies actually to the area of any boundary separating a region of space. So it applies to any finite region of space, basically. So the entropy of this finite volume should be, the expectation is that it is actually given by the area of its boundary. But the question is really, how do we justify this conjecture? So I will use the methods of Gibbons and Hawking from 1977. So they derived the entropy of black holes using a saddle point approximation of the Euclidean path integral, gravitational path integral. And what we want to do is we want to write down a similar gravitational path integral or partition function for finite volumes of space, and then take a saddle point approximation and then derive the entropy. And we will do this by using the method of so-called constrained instantons or constrained gravitational path integrals. So the difference with their work is that we have to impose some constraint to fix the size of this region. Okay, so let me briefly review what Gibbons and Hawking did. So they represented the thermal canonical partition function in gravity by a gravitational path integral over Euclidean metrics, where I is the Euclidean action, say for GR. And then they take a saddle point approximation, and in that case, if the on-shell action is much larger than h bar, then you can approximate the partition function in this way, as we have heard many times. Now they applied it to black holes, but also, in fact, in their original paper already to Euclidean de Sitter space. So Euclidean de Sitter space is a round sphere whose radius is set by the cosmological constant or by the de Sitter curvature scale L. So it has topology as D, but it's actually a round sphere. And if you evaluate the action of general relativity plus cosmological constant, positive cosmological constant, if you evaluate that on this saddle, then you get minus the area over 4g, so minus the de Sitter entropy. Now, what does this computation mean? It means actually that the partition function is in this zero loop saddle point approximation is equal to e to the s. And how should we interpret this? Well, since de Sitter is a compact space, Euclidean de Sitter is a compact space, the energy is actually zero, because energy in gravity is always defined on a boundary. So the energy is zero, but this means that, so energy is zero, but this means that the partition function is just trace of 1. So it's trace of 1, so this is actually over the entire Hilbert space, so it just computes the dimension of the entire Hilbert space. So one way to think about this answer e to the s is that it is equal to the dimension of the Hilbert space of states surrounded by this cosmological horizon. Okay, so that was the Gibbons-Hawking computation. So now we want to generalize it to finite volumes of space. And as I already mentioned, in order to talk about a finite region, we have to somehow fix its size. And one thing we thought about is fixing the area, but that didn't work. And so what we did is we fixed the spatial volume of our spatial region. And so we impose an extra constraint in the path integral that fixes this volume V. Now you can represent this delta function in a different way using a Lagrange multiplier. So then you get an integral over the Lagrange multiplier and then an extra exponential. So e to the lambda and then c minus v. So c is the constraint. Okay, so now we will just do this where the Euclidean action is given by general relativity. And yeah, so lambda is imaginary, so it's along the imaginary axis. That's correct. Okay, so before I do this computation, let me first mention what the metrics are that we integrate over. So what are the topologies that we integrate over? So what we do is we consider a topological d-1 ball. So big D is the number of space-time dimensions. So a codimension one topological ball whose boundary has the topology of a sphere. And since we work in Euclidean signature, we want to rotate this ball around the Euclidean time circle, but the boundary should be a fixed point. And if you do that, you get the topology of a D-sphere, just like in de Sitter space. And one way to visualize this is in 2 dimensions, so 1 + 1 space-time dimensions. So then the ball is just a line, and the boundary, the S0, is 2 points. So if you rotate this line along the Euclidean circle by fixing these 2 points, you get a 2-sphere. And this generalizes to higher dimensions, so then you get a D-sphere. Okay, so now this is our partition function represented as a constrained path integral where we have this lambda, and we will look at the situation where the action, there's some low energy effective field theory where the action is given by GR, and we also allow for a cosmological constant. And what we do is we foliate this ball, we foliate the sphere by d-1 balls, as I already mentioned, and they are at constant phi. And we impose the condition that for all constant phi slices, the volume is the same. The spatial volume is the same. So this gamma here is the induced metric on this slice, and n you can think about as the lapse. So now what we have to do, what we do is we take a saddle point approximation, and in that case you get the Einstein equation from this part, but you get it. It's actually sourced by an effective perfect fluid because of this term, and the perfect fluid has vanishing energy density, but it has a pressure. So the saddle point equations take this form where the stress tensor is that of a perfect fluid with pressure given by lambda over n. All right, so now we will look for solutions of this saddle point equations, and we will just look for the simplest solutions that you can think of: static, spherically symmetric solutions. And these are the solutions. So for lambda is 0. We also have solutions for a positive and negative cosmological constant, but this is like the simplest solution you can think of. So the spatial metric is completely just flat, just Euclidean space. And this is the time component, Euclidean time component. And notice that it has a horizon at R is RV, where RV is set by the volume big V. And this saddle has topology as D. It is conformally flat, in fact, but it has a curvature singularity at the horizon, at R is RV. Now, even though it has a curvature singularity, you can compute the Euclidean action You can take it on shell, and it's actually finite. And if you do that computation for a zero cosmological constant, but this generalizes as well, you get minus A over 4G. So you get precisely the Bekenstein-Hawking entropy in this saddle approximation in the zero loop approximation. And so this generalizes the Gibbons-Hawking partition function to a finite volume of space. All right, and as I said, there's an interesting generalization to other, to positive or negative cosmological constant, but you get the same result. Right, and in a specific case, actually, where the volume is equal to the de Sitter static patch, you obtain the result of Gibbons and Hawking. So in that sense, it's really a generalization. Now, to conclude. We talked about we constructed the partition function for a volume of space, and we argued that it is actually the dimension of the quantum gravity Hilbert space of a topological ball of fixed volume, fixed spatial volume. And in the saddle approximation, this Hilbert space dimension matches with the Bekenstein-Hawking entropy attributed to spatial regions. So we get e to the A over 4G. And for future directions, we would like to understand this curvature singularity better and perhaps see whether higher curvature corrections regularize this singularity at the horizon. Thank you.
Thank you. Any questions?
Thank you for the nice talk. I'm just wondering, compared to the standard approach where you just periodically identify the Euclidean time to get rid of the conical singularity.
Right, we also do that.
You have done this already, and now you just have a different curvature singularity that you still need to do.
Exactly, so the conical singularity is removed, but then you still have a curvature, another curvature singularity.
So in the usual approach, I think you know, in the saddle point approximation, it's like an effective field theory thing. You have Einstein-Hilbert, and so you don't want to include singular geometries because presumably if the curvature is very high, you would need higher curvature corrections already in the action to account for those. But now you have a singularity, so is that consistent with your use of Einstein-Hilbert without any correction?
Yeah, that's a very good question. So it would only be consistent if the higher curvature corrections somehow smoothen out.
Okay, so they have to cancel out somehow from. Okay.
Yeah, and we still have to investigate that.
Right, thanks.
Yeah, thanks for the talk. Just a quick, maybe naive question. So it struck me that you look at fixed proper volume again, and in this first derivation of the Einstein equations from entanglement equilibrium by Ted, we also used entropy variation at fixed volume, and in that derivation, although it's a bit question why one would have to fix the volume. Does your approach here shed any new light on it? Because I guess you can use that partition function to vary it and then plug it basically into his old proposal, right? Exactly,
yeah. So we believe that this could give a proof of that conjecture by Ted.
Okay.
Precisely because in fact, of course, this work was motivated by Ted's original work. I didn't mention that, but precisely because he fixes the spatial volume, and we get the entropy. We get the entropy for this fixed spatial volume partition function, and actually it's the entropy of a maximally mixed state. So adding matter, for instance, should lower the entropy, and that's precisely his conjecture, namely that the entropy of the vacuum is maximal at fixed spatial volume, and that if you add matter then or curvature, then it lowers the entropy.
Okay, yeah, very nice. Look forward to more. Sorry.
Yeah. So no, we have to investigate that more as well. And one of the open questions in that conjecture was whether the entropy of the vacuum is maximal or minimal. So you can prove from GR, if you look at first order variations, that the entropy is stationary in the vacuum, but it doesn't tell you whether it is maximal or minimal. And so this suggests that it is maximal, but we would like to understand it better.
Yeah, very nice. I look forward to hearing more about that.
Okay, so let's thank the speaker again.